afternoon, everyone. Am I audible? Not audible? Last bench? Audible? Okay. So, I'm Dr.Prateek Sharma. I'm working as assistant professor in electrical engineering department at IIT Tirupati. So, today I got an opportunity to interact with you. I'm seeing a lot of faculties and students as well who are interested to see in the VLSI domain what are the new things going on. So, as per our discussion with Dr. Shakti sir, so I'm going to give a talk on artificial intelligence in VLSI domain. So, earlier I did my master's and my PhD in analog and high-speed mixed signal design. And thereafter I joined Global Foundries in Bangalore. So I worked around 4 to 5 years there, and then I moved here. So I will try to make this presentation as more interactive. So you just stop me wherever you want if you have any doubts. So just feel free to make this interaction very interactive. So that's what I expect. So I have divided this presentation into halves. So first we will be getting more towards AI in analog design field. So overall VLSI, as you know, it's a very wide and it has a lot of application and a lot of areas. So analog IC and mixed signal IC is one of them. So since I am working in analog field, so I will be telling about what is the role of AI in this area. And the second half of the presentation I will divide into the advanced packaging. So we will see in next 20 years how this semiconductor industry will go and what are the roadmaps and the future aspects for the semiconductor industry in the next 20 years. So that's why I divided this presentation. So why AI in the analog IC design? So the first fundamental challenge, if you have seen in analog IC design, is the design complexity. So like your digital design, it's not very straightforward. It requires a lot of knowledge on the analog circuits, solving the circuits, and also from depending application to application, there are different circuits, different architectures, different topology. So it is very difficult to adopt AI in the analog area. So right now we are seeing more AI application in the digital designs, not in analog designs. So as you know that analog design, for example, a common source amplifier, basically it's an amplifier, and also it involves a lot of application on the device knowledge. So from top to bottom, top level to bottom, there is a lot of it is almost interlinked. You start with your schematic, go for the layout, then do the post layout, right? So it is involved a lot of stages, and there are a lot of things involved in that. So that is why it is very difficult, and all those topologies and all those constraints are very interconnected. It is very difficult to analyze in analog area, and it's not very straightforward, to be frank. And there are a lot of gaps right now in the EDA tools. So right now, if you came to know what are the different EDA tools, like we have Synopsys, Cadence. So there are a lot of tools, and there are a lot of gaps involved in them. So unlike your RTL to GTS design, in digital side, analog is not very straightforward. Depending on the application, we try to see what are the tools we have need to use. So right now there is a lot of gap in this market as well in the EDA, and we are seeing a lot of AI models right now, like LLMs and CLNs, so neural networks. So they are very high process or advanced models, and that is how we can try to use those models in analog IC design. So that one of the major application we can include is like optimization of the circuit. So we have one circuit, and it is very difficult in the real time to optimize the circuit. So you make a schematic, and then you make a layout, and in then you find out there's some parasitic come in the layout, and you do not optimize that. You have to go back into the schematic, retune the design. So that is a very lot of challenge. It's a very hectic job. So there is something we can see there is an AI can play a role where you can do the optimization show from system level. If we start with the system level, we can go with the circuit level and the device level. And each and every stage, they are all interconnected to each other. So somehow if designer screw up in the circuit level, he will not get the system level specs. So somehow all three stages are very interlinked. So you start with your system requirement, then you select your topology, then you do the circuit sizing, then you generate the layout, do the post layout. So these are the different steps. So now what happens when you optimize in one stage, you may find that in the system, one stage above or one stage below, it is screwed up. So that could also possible. That is something we can include the AI in the scope. Because when we optimize, we will optimize all together, considering all the stages together. So this is how we can include the AI in this one analog design. So as I told earlier, analog is not very trivial. It's not easy as compared to digital, I would say, because it requires a lot of knowledge on the analog side, and there are a lot of parameters, there are a lot of topologies, there are also the device models and the parasitics associated them, layout challenges, and the floor planning. All those things we need to take consideration while doing the analog design. So in industry as well, we have a lot of engineers who are working on the schematic side. There are a couple of engineers who are designing the layouts and so forth. So all these stages are interlinked together. So once you start your schematic first, then you have to optimize it such a way that when you do the layout, you should get your desired spec. So while designing the schematic itself, in your mind it should be there that some parasitics would come into your layout, and you have to account these parasitics into your design. This is how you should proceed. And this is a very good case of the analog design in the AI, the role of AI we can do. So what are the bottlenecks? So if you go with the AI in the analog design, what are the bottlenecks? So in analog IC design, it's not scalable like your digital. So when you transfer from one technology to another, it is not direct straightforward. You cannot directly scale the design when you go for the lower technology. Suppose I am designing an amplifier in 180 nanometer, and now I want to go for 65 nanometer or let's say 22 nanometer. So it's not directly, you just have to scale the W by L and look at your design results. It doesn't work like that. So in the most challenging job in analog is not scalable as the digital is. So that's also one of the reasons we have. Till now, any questions, anything? So as we are discussing the challenges, right? So one of the main issue in this analog design is the scaling. So they are not scalable like your digital design. So when we are designing from one technology to another, it's not purely scale the W by L ratios into your design. So a lot of things happen. Another thing is the simulation cost, right? When you do the analog design optimization, so it requires a lot of resources. As you heard about your GPU processing, right? So it requires a lot of memories. Same like when you do for the AI with analog design, then you require a lot of memory and a lot of area. And every stage you need to optimize your design. So that's why it requires a lot of simulation costs or resources. And adaptability, right? So how AI can adapt your analog design? That is one of the biggest challenges right now we have. And it is not proven yet. So we are seeing a lot of papers coming in the analog IC design with AI, but we don't know how it will go forward. In the next 5 to 10 years, it will be very crucial to know how this AI will perform in this area. So this is one of the examples. So this is called Berkeley Analog Generator. So it is very open source tool. You can find out it in the internet. So this group, the Berkeley from UC Berkeley, University of California Berkeley group, they actually designed an analog generator. So what they do, they created one Python-based script. So from the script, and they optimize the network, and then they will produce directly your GDS or the layout. This is how they build a framework. So this was the first paper come back in 2013, not recently. It was started in 2013. So they started one script, they performed different, they selected few topologies like common source amplifier, differential amplifier, some basic ADCs. So from netlist to layout, they created through this Python script. So this was the first paper came into this. So this is how they basic block diagram. So they took the design, they actually parameterize each and every variable in the schematic, and then they optimize these variables using the AI or the algorithm, and then finally it will just after you optimize your design, you will get a layout. So from specification, all the technology file. So these are the inputs which you feed into this generator, and then you will get your design. So this is another work, auto circuit. So this is also you will get on the one group from the University of California. They demonstrated this in this paper. They actually this is much faster than the previous one, and also they are taking the schematic netlist and then producing the direct the layout based on all the design variables. So this is how the people have started going in the last 5 years. So this was published in 2020, around 5 years back. So they explored different algorithms, and also the 90% some good. If you compare with the simulation time between this and the previous paper, it is much more faster than that. And this is one of the recent work. This is something called Align. So it is from University of Princeton. So they actually give you very direct optimization of analog design from SPICE netlist to GDS. So you just need to give your SPICE netlist, and it will optimize the layout. So they will do the optimization in the layout level. So there are, as I talked, so there are different levels of optimization you do. One is on the schematic level, another level of optimization you do in the layout level. So, and there are different layout possibilities. So somehow they figure out that there is a gap. So they feed the SPICE netlist, and the programmer or the AI algorithm work in such a way that they will just directly put you the GDS2 file. And this is another machine learning guided layout. So all these are talking about the layout generation from the SPICE netlist. So they optimize your network or the circuit, and then they will give you the optimum layout for that. And this is how this works. So there are different design rules, different parameters. They feed into this algorithm, and then finally you will get a GDS. The final end product should be the GDS, which is more optimized and which meets all the desired specification. So this is how people have demonstrated recently in 5 years how we can use the AI in the real analog IC design, and then we can exploit the AI and do more level of optimizations. And this is another recent work. So if you see on the top left hand side, these are the very fundamental transformers or inductors we design in the IC level. And I think most of you have heard about the filters, basic filters. So how we design the filter using LNC, inductors and capacitors, right? So somehow we use these inductors in our designs for designing the filters. And on the right hand side, if you see this arbitrary shape, some kind of that doesn't make any sense, right? Seeing this layout, but somehow this layout is working because it is AI generated layout, and this group claim this is more optimized. So this is very traditional way of making the filter using inductors and capacitor, and this is what AI generated. Very unconventional, which you will not find in your textbook, but gives the performance and more optimized. So this is the final chip photograph. If you see, it's more like if someone looks at it, it's more like a QR code or some kind of a garbage design. No one will recognize how it will work. But somehow this is working as a filter in the power amplifier. So it has no design rules, no design equations, nothing. It is just simply generated from the AI. So AI tool learns from different layouts and then finally it will give this kind of a structure. Yeah, similar to this one more paper, they designed one deep power amplifier in the design. So power amplifier is, I can say that it's the last block of your transmitter stage. It is one of the block you can say. I think you have all heard about different types of power amplifier. So they designed for high frequency deep band power amplifier using the AI. So they started from the design specs and they do the behavior modeling of the different blocks, then the physical layout, and then they feed into the simulation. So this is how they start with the design spec and with the physical design. So the end goal of the AI is to reduce the time of the engineer to optimize the design. So every time when an engineer designs some kind of analog block, he has to optimize in the schematic level. And then once he do the optimization, he move to the layout. So again he has to do one more level of optimization. So after that he realized that he has to do some optimization again back to the schematic. So this going forth and back requires a lot of time, lot of effort. And in the end it's not very sure that you will get a very optimum solution for this analog design. So this is how people are more exploring this AI towards the optimization of the analog designs. So this is right now in a very early stage. In recent 1 or 2 years, there are a lot of papers are coming in analog IC design, because analog is something which requires a different skill set, different kind of people, and also it requires a lot of knowledge on the circuits and very intuitive. No one has expected that how AI can penetrate this market, but somehow it is shown that the AI has a lot of potential working in the analog area, because there are a lot of optimizations the engineer do in his life. So this is how the people are exploring in the analog IC design, and also there are EDA. EDA side is another one thing that people are exploring. So it is very new in the market, and we have to see in the next 5-10 years how the things will change. But definitely it's going to have a major impact in our area. So this is how I planned. This is my first half, because AI is a very new, very niche area, and there are a lot of things are going on. As a group in IIT Tirupati also, we are working few things on the AI in VLSI side. We don't have very large scalability right now in the market as well. So it is very niche. So I try to constrain very limited on the AI side, and next we will proceed toward how the semiconductor industry will grow in next 20 years, what are the changes will be done, and how we will predict what the market is going on in the semiconductor side. So especially on what are the basic things we will see in our mobile phones. That's what I am talking about. So let me know if you have any questions till now, so that please let me know if anyone has any question, then we can proceed further. Okay. Anything? Okay. So this is how I divided the contents. So overview, the introduction of the MOS basics, and how the semiconductor technology will go, and more. My presentation will be included toward the 3D integration. I assume some of you are hiring this 3D IC, heterogeneous integration. There are a lot of things you are hearing about, right? So this is how I will tell about what are those things and how this will impact the semiconductor industry. And there are some few case studies in different areas like silicon photonics and wireless communication. So this is how our semiconductor market is growing up if you compare, right? So globally, if you see if you compare by 2033, it will have almost 7% annually growth rate, and these are how the market divided into different streams like automotive, wireless, and your internet, So it is actually growing very fast compared to other streams. And this is one I picked up from one mobile phone. This is one Qualcomm series modern chip. So can anyone tell me what are the things inside in this chip? Just if you are interested to guess what are the things that are there in this chip. Anyone? Transistor is okay. Finally, it's transistor only. But I am just trying to what are the blocks? What are the circuits? What are the blocks it has? So this is a Qualcomm flagship processor, Snapdragon. You can just tell what are the things in there. So these are the things. It has memory, logic circuits, power management IC, digital circuits, analog circuits, RF transceiver. So these are the different areas. So even for the students, when you graduate and if you work for some industry, you will be working in any one of these fields. Okay, so there are different memory, logic designers, power management IC, digital, analog and RF circuits. It's a complete modern or the Snapdragon processor that you will have. And these are the different companies. So in our VLSI, we segregate, differentiate company by product companies. So like Qualcomm, Intel, Nvidia, TI. So there are some IT companies which will provide you the IP as a third party. So Cadence, Synopsys, Rambus. And these are the foundries, so where you fabricate your designs, so like Global Foundry, TSMC, UMC. And there are some service companies like, these are called fabless companies, so like RFIC, so a lot of startups are growing in this service company. And finally the EDA companies who are providing the tools for the simulation like Cadence, Synopsys and different. So this is how we divide. So there are some ASIC, SoC or digital IC designers who work, and there are some analog and mixed signal designers and RFIC designer. So once you graduate, so if you are interested to work in VLSI, you will be working in any of these areas. So you may be an SoC designer or AMS designer or RFIC designer. So among them also there are a lot of applications and spaces are there. So this is how we start for analog and RF circuit design. So this is how we start. We start with a schematic, we do some circuit simulation, then we do the layout, and once the layout is done, we extract the parameters. We do the post-layout simulation based on the extracted parameter, and then finally we generate the GDS. So this is the complete cycle, starting from the schematic to the layout generation. This is how we proceed. And this is one of the work I did during my PhD. So this is one fabricated RF transceiver. So it was done in 130 nanometer technology. So this is a chip photograph you can see. On the right hand side, this is the packaged form. So this chip is packaged into QFN package. So you can see there are some wires going on. These are called bond wires, which are mounted, which are used in the packaging. So you put the IC in between, and there are some bond wires. Then finally, when what you see is the packaged IC in your PCBs or different motherboards. This is another one. This is one the IC, the IC or the chip, and then we packaged it, and this is how we soldered on the PCB. So this is your PCB, which maybe everyone knows. We soldered this packaged IC, and then we test out in our lab. So let's start with the MOS basics. So this is a very fundamental MOS transistor we have. So there are different regions. When we start with the triode, pinch off, and then saturation. So this is how we generate the ID versus VGS curve. So mostly we are located when we are operating the transistor as a resistor, we operate in the triode region, and once it crosses the pinch off, the saturation region comes. But the main challenge in the MOSFET design is there are a lot of parasitics if you see. So these parasitics or the capacitance are very killer of the design. So they will harm the design in. So we will come to know how they are going to impact the performance, but this is how the structure of the cross section of the MOSFET, and in the saturation region these are the different capacitors will come into the picture. So this is how the MOS transistor we have, and this is the small signal model of the MOSFET. And then if someone wants to calculate the FT, which is nothing but unity gain frequency, this is very fundamental or important aspect of a transistor. So that is nothing but the output current, which is short circuited at the output node, and the ratio between the output current to the input current, that gives you the FT, and which is directly proportional to your transconductance and the source to gate capacitance, and also the gate to drain capacitance. So FT is one of the major parameters in the VLSI technology. So there are a lot of people have shown, if you go through the data sheet of any technology, any semiconductor technology, one of the major factor or one of the major parameter which is already mentioned is FT and Fmax. So this is how we quantify how this technology is suitable for high speed operations or high speed applications. So if you want to operate your design at very high frequencies, somewhere in 100 gigahertz, 200 gigahertz, so then your FT and Fmax should be almost 10 times or at least 5 times should be your operating frequency. This is some thumb of rule we can go for. So these are the capacitance, also there is some resistance, and when we go for the higher model of the gate, there are some inductance also we will find. So when you do the RFIC design, you need to take all these parasitics into your account, and then you will need to design, and then we extract all these parasitics from the layout. So one of the major, just now I told that you will FT, which is nothing but unity gain frequency, or the frequency for which current gain is unity, and other important factor is Fmax, where the power gain becomes unity. So these very fundamental parameters of any semiconductor technology, which is very important for your high-speed designs or RF integrated designs. Another important parameter is a gain bandwidth product. So somehow when you design your op-amp or any amplifier, you always heard about gain bandwidth, gain bandwidth. So this is very fundamental parameter. This is how it will tell you how faster your circuit is. So, and almost this gain bandwidth in every design, right, it is limited by some technology number. So this gain bandwidth of your any analog circuit which you design in your course project or your major project, so every time it will be limited by your FT. So there is a direct relation between FT and your gain bandwidth product. So if you want to design any circuit with higher gain bandwidth product, you need to increase your FT of the technology. So let's move to what are the motivations. So what are the roadmap or what are the requirements in the next 20 years? So these are the two lines. So if you see this orange line, this is the wireless line. So this tells about your speed of your mobile phone. On the x-axis we have the year. So as we are moving forward, what is the requirement from your mobile phone, and this is your wire line. Wire line basically your broadband or your optical fiber internet. So this shows what is your requirement. So as we are standing somewhere here, just to in 2020 it is almost like 1 Gbps the requirement of your wireless. So we extrapolated these two lines, and in the next 20 years, in 2014, both of these two lines will intersect, and the requirement will go up to 1 Gbps. So this is how the prediction is. So in next 20 years, it is expected that the requirement from your mobile phone internet and also your broadband internet, it should go around 1 Gbps in speed, and which is almost, we say that 1000 times currently what we have right now. So this is a very fundamental Shannon's law. Many of you have studied in your communications. So it denotes what is the maximum channel speed with respect to the bandwidth and signal to noise ratio. So if you take an example of Wi-Fi 6, considering the data rate and the bandwidth, and let's assume the signal to noise ratio to be 10. So you will find out the capacity, the maximum capacity you can achieve is 0.5 Gbps. So right now, currently we need, if you go back, so we require almost 1 Gbps right now, and now we can only achieve 0.5 Gbps with this example, with this assumptions. So this is the major challenge. So this is how we require almost 20 times more speed. So how can we increase the data rate? So one of the way is more bandwidth. You can increase the bandwidth, but that is not something allowed, because if you work with the wireless communication for mobile, so we have different bands, and each band have different channels, and each channel is fixed bandwidth. The bandwidth you cannot change. So you have to define more number of complex modulation schemes. You can increase the higher data rate. You can go for different modulation schemes like COM64, COM128, 256 COM. Like that you can increase. Other thing is carrier aggregation. So you can use different carriers into your communications, and then you can exploit the bandwidth. And the fuel duplex and MIMO is another way. So MIMO is something you require multiple inputs and multiple outputs, and finally you get a more bandwidth or more data rate from using this multiple. So you might have seen different Wi-Fi's have 2 antennas in their system. So this is how they are trying to increase. They are trying to double the bandwidth using 2 antennas. So going forward, this MIMO will be more applicable into the wireless communication. So there are different applications, space like SATCOM, satellite communications, where we are using the different dishes with lot of antennas, so that we can increase the bandwidth of the system. And then always it is better to move towards the higher frequency range. So when we move towards higher frequency, like D band or G band, so these are the millimeter waves, so more than 30 gigahertz. So when you go for higher band, higher frequency, you can get more bandwidth. So there are other challenges which will come in that. So any question, anything? I think no one is on to ask. So this is a very fundamental Moore's law, which I think many of us, when they study VLSI design, I think this is taught in the first chapter itself, and it is a very famous scientist who actually incubated the Intel. He is the when you work in Intel, you will came to know he has done a lot of contribution in the Intel. So he tells that every 2 years, so the number of transistors gets doubled. So this is how it is shown with on the x-axis the time, and on the y-axis is the number of transistors at per chip. So as per the Moore's law, every 2 years your number of transistors should be doubled. So this is how we see the trend recently, but somehow in the recent time this trend is not seen, because when you go with low technology nodes like 1 nanometer, 2 nanometer, 3 nanometer, what next we can go for? That's the very fundamental challenge the designers have. There is a very hard limit when you go with 3 nanometer, 2 nanometer. So beyond that, it's very difficult to go with that. So the Moore's law, somewhere it is saturating, but there are a lot of opportunities, different ways are there where we can exploit the Moore's law, where we can use the Moore's law itself. We will come to know how we can, even with the lower technology nodes, how this law is still applicable. This is how we have introduced different type of transistors. So in 2011, the Professor Chen Ming Hu from UC Berkeley, they come up with the FinFETs. So we have a transistor, normal MOSFET transistor, which is a planar device. So this FinFET is actually the 3D device. So they introduce one more dimension into this, and that is number of pins and the thickness of the pins. So this is how they shrink the MOSFET transistor in one dimension, and they increase the size in other dimensions. So it's a 3D type of a MOSFET, and this is very used when you design the in 3 nanometer, 5 nanometer. In some nanometer, this is the device which we are using, not the traditional planar MOSFETs. So if you are following different news, so this is another type of new device which is rolling up recently. This is gate all around FinFET. So I think the TSMC has doing a lot of work on this. When you design for 1 nanometer, 2 nanometer, this is the device they are fabricating. So it's again a different type of the structure which can fetch you more performance inside. And this is the complementary FETs, basically the two NMOS and PMOS. So they're designing on the same one. If you see, NMOS in the bottom side, PMOS is on the top side. So something like that. And again, then this is very futuristic. That is 3D VLSI. They are trying to fabricate. This is thinking to fabricate different transistors in different levels, not on the same plane, but on the different planes. So this is how the evolution of different transistor happened in last few years. So this is just I plotted on the log scale the number of transistors. So if you see from in the next 20 to 20 years, it is almost as per the Moore's law, you require 1,000 times more transistor compared to 2020 to 2014, almost 1,000 times you require more transistor as per the Moore's law. But what happens to the gate length? The gate length is almost fixed. So when you go with the gate length, if you recall, you start with 180 nanometer. Let's say we start with some 1 micrometer, we come with 180 nanometer, 90 nanometer, 65, then it will saturate to some 20 nanometer. So the gate length of the transistor always fixed beyond a point. So if you talk with the some 3 nanometer, 5 nanometer, it's not actually the gate length. So this is almost fixed going in years. And this is how when you scale down the technology, these are some second order effects like channel and modulation, velocity, saturation. So it starts increasing. So when we are in early days, when we are working with 1 micrometer technology, there are very minimal, we can say second order effect. When we go with lower technologies like 10 nanometer or 20 nanometer, there are a lot of second order effects we will face. And this is how we plot the FTF max. So FTF max will increase with the scaling down the technology, but beyond a point it will again saturate. So in 20 nanometer you may get maximum peak FTF max, but after that again this FTF max will saturate because of the parasitics in the design. So somehow if you narrow down the transistor, you will get a lesser parasitic, but finally when you go for the routing, there will be additional parasitics which will come into the picture, and that will degrade the overall FTF max. So this is why this is degrading. So as an RF designer, I will be happy to use 20 nanometer technology because it gives me very good high FTF max. And when we go to the analog designer, we always choose to some 10 micrometer because we don't want to see channel length modulation or velocity saturation effects. And for digital designer, they are more regressive towards the lower technology node because for them it's all about the performance. So we call it PPA, power, performance and area. So that's why the digital designer will be somewhere there. So if you see, there are 3 types of designers and they want to operate in 3 different technology because of their application and their requirements. So any doubts? This is very fundamental. Anything? Any doubts? In this one? In this one, there is no role of AI such. See, this is very fundamental. We are studying the effects, or we are trying to make a roadmap in next 20 years. So in next 20 years, how this Moore's law will be satisfied, this is what we are trying to see. Finally, the AI will be like a assistance. So AI will never capture this VLSI totally like computer science. It is totally independent of the designer. But in VLSI, it will be mostly like an assistance. So we will be requiring AI for our optimizations for our design. So in the end, it's the designer who will do the entire job, but the AI will assist them. Somehow it will reduce their time, somehow it will provide more resources, it will be So when we talk, let's compare the time in 1970s where designers don't have any simulations, anything. So what they do, they just fabricate their design, they test it in the lab, and they estimate based on the device model. They just estimate this is the performance we get. They come back to the foundry, they just manipulate some parameters, and then again. So this is how, without simulation, this is how their life is because of no simulation. But when we are living in the age of AI, it will be more easier for the designers. This is how we will proceed. So this is why is it only the FT? Right now we are talking about the FT max. So this is we need to see the only parameter we are saying the FT. Does it very important parameter? We will see the answer. So this is ID versus VGS curve. So somehow it is not visible. So there is one very slowly, if you see, when you start increasing the VGS, the current is initially 0 and this starts going up, and you will be in a weak inversion region where the characteristics will be the exponential. Once you go to the strong inversion, it will be the square law will be followed, and then velocity saturation, it will be a linear. So this is how in weak inversion it is exponential, quadratic, and then linear region. And you will see there are two parameters. One is the GM, the transconductance, the overall transconductance, and one is the GM by IT. So what does it mean by GM by IT is how much transconductance you can get from a unit current. So that gives you the efficiency of the device. So GM by IT is another parameter. So when we talk about the weak inversion, so overall GM you will get is very minimal. So it is very less. But when you go for the GM by IT, it is best in the weak inversions. In case of strong inversion region, which is the square law in region here, it is always some scan minimal or in between. So moderate you will get GM by IT, and GM you will get. When you go with the velocity saturation, you will get the best GM. You will get the highest GM. But the trade-off will be that you will get a poor GM by IT. So when we go to the lower technologies, this is how we are somewhere there. So we always operate our device in the velocity saturation. We will get a good GM out of device, but very poor GM by IT. So we will see how this will impact. So this is just to show the transconductance versus VGS. So the earlier I have shown you the ID versus VGS. When you differentiate the ID, you will get the transconductance. So GM is ID versus ID by VGS. So if you differentiate this, you will get this characteristic. So this shows how your L channel length decreases. So the bottom one is the longer length device. The top one, this one is the short or more narrower device. So if you see the threshold of all these three technologies is almost fixed. So this is same. The threshold is this is a very fundamental limit. So we can derive from the equation. So this is very fundamental. So this is fixed. And now when we go with the lower technologies, you will see that we can achieve higher GM. On contrary, with the longer devices, we are getting lower GM, as we have discussed earlier. But what is the trade-off? If you see, the moment you on the transistor, it directly jumps into the velocity saturation. There is no time it goes into the strong inversion region. So it will directly move into the velocity saturation. So if you see this region, this range, it is actually reducing. On case of higher gate length device, the range is very higher, but when you go with the lower technology, it is very less. So this is one trade-off. When we go with the lower technologies, this is why we are seeing the performance issues with this. And these are the different equations we plotted. So this is the FT equation when we with higher channel device, when we go with some 180 nanometer, 90 nanometer device, if you see FT is inversely proportional to L square. Okay, and when we go with the velocity saturation, where is dominant in lower technology nodes. So this is how FT is inversely proportional to L. So rather than L square, it becomes L. So it means that if you scale down the technology beyond a point, you will not get that much improvement over the FT side. So this because of the velocity saturation effect. So in our lab, we as a practice, we designed one power amplifier using NFET device with a width of 1 mm width, and it is biased at 0.5 volts. And what we do, we find out the output power versus P in, and we sweep the input power with respect to P out. So we know that the amplifier we are designing in our system is linear. We assume that it's linear, but it's not. Actually, it's non-linear device. The MOSFET is a non-linear device. Beyond some point, you will see the non-linearity. At small signal, at very small power, at the input, you will see a very good relation. Like you see a very good linear relation between input and output. But beyond some point, it will saturate. It will not increase. So this is called non-linearity in this. So if you observe between 150 nanometer and 20 nanometer device, the comparison, you will see, you will get a more output power. Yes, definitely you will get more output because your GM is more in that device. But what is the trade-off? The trade-off is you cannot operate at higher power. So if you see, you will be somewhere in -10 if you want to operate this 20 nanometer device. And if you go with this device, you can operate with plus 10 dBm. This is the difference. So earlier I just said that in lower technologies you will get more transconductance, but the range will be limited. This is how we demonstrated. You get a more transconductance. On the right hand side you can see more transconductance, but finally when you go to some level it will drop some due to velocity saturation effect. But here you will get a lesser transconductance, but it is more linear. It will be more constant. So this is one trade-off you will get. And the power amplifier is one application where you require more linearity. In sense, you want to cover the more input power level. So you don't want any amplifier to saturate at -10 dBm at lower powers. You want to cover as much as possible. So that's what this lower technology is not much useful in such applications. It is the linearity which dominates in the factor. So apart from just we discussed about the AI and what are we seeing the trends in the semiconductor industry, one important thing which we are going to see is the packaging or the 3D integrations. So we will right now using different packagings, if I will discuss. Going forward, we are more concerned about the 3D packaging, 3D IC designs. So this is how different 3D system in package, system in SoC, IC design, and this is how the interconnects. So between the two ICs, we need some interconnects. This is how the interconnect scaling happens. So over the time period. So the people have demonstrated 100 nanometer pitch for the interconnect. So these are the different schemes we use for. So for example, this is a 2.5D. So there are two dies on the same plane, and we use to wire bond. So this is called 2.5D kind of a packaging. And then we have a 3D where you put one die on top of other. That is called 3D one. So these are the different packaging, different types of interconnects which we use, and these are the different timelines. With the timelines, how these interconnects sizes are reducing. So these interconnects are very important from time to time when we have to connect two different ICs. These have to offer a minimal parasitics, and also they have to be very narrow in their dimension. This is how different kind of hybrid bondings and the TSPs are used. This is a die to wafer where you there is one die and one wafer, and you try to integrate with them. There is wafer to wafer bonding, and there are different hybrid bondings as well. So in 3D packaging, there are different packaging types we have. So these are the three ways: die to wafer, wafer to wafer, and hybrid bonding. And these are the different materials or different combinations we can use. So most fundamental is the silicon. So we have silicon, germanium. There are third and fourth group elements like gallium arsenide, indium phosphide as well, and wide gap semiconductor like GaAs, silicon carbide, and also some element gallium nitride and the diamond. And these are the different devices. So these are the materials and different devices formed from these technologies. And these are the different process or packaging type we can use to integrate. So the main idea is when we go for 3D integration, we will integrate two different types of technologies. Maybe some, you take an example such like silicon with silicon germanium, or some silicon with gallium arsenide or gallium nitride. And these are the different applications. So logic, memory is one. In memories, we require a very low technology CMOS process because memory space is very high. It requires a lot of area. Analog and RF is another space where you require high FT, high FMX technology. And photonics, RF photonics is one thing. And the power, and for the power management ICs. So, any questions? So let us, as per our content, let us go to the one case study, that is nothing but silicon photonics, case study 1. So we are going to see how this packaging work will impact this silicon photonics. So this is, if you recall, I think most of you have seen this amplifier. This is basically a common source amplifier. I put a feedback in the shunt. This is shunt feedback amplifier. And it is called a transimpedance amplifier. So idea is to convert the input current into the voltage, and the current is given from the photodiode. So the photodiode input is the light signal. It converts light into the current, and then current is fed into this amplifier. So this TIA is designed on different processes like CMOS and silicon germanium. So this is a BJT based. So we need to design it on silicon germanium device. And this photodiode is a different device altogether. It cannot be fabricated with this one. So people have demonstrated two different types of solution. One is the hybrid integration, right, where you have photodiode on a different IC and your amplifier on the different IC. So you integrate using some hybrid technique or packaging technique. Other thing is monolithic integration, where you combine all these photodiode and photodetector on the TIA on the same die. This is called monolithic integration. So a lot of industries are investing in both of these directions. There are some pros and cons associated with these two techniques, which will be studied. And just like photodetector, it's used on the receiver side. On the transmitter side, we have a driver, just like TIA. And other thing is the electro-optical modulator. So modulator is used in the transmitter side. So these are the bandwidth equations. It is fundamentally dependent on the FT of the technology. So for this TIA design, if you want higher bandwidth, you need higher FT of the device and also less number of parasitics, that is this input capacitance, so that we can get better bandwidth. The main differentiation point is the hybrid integration is when you go for hybrid, then you require some interconnects. The interconnect comes with their own parasitics. They will include into the design, and this parasitic capacitance will reduce down your bandwidth. But in case of monolithic integration, there are no such parasitics, and then you will get higher bandwidth in the monolithic side. So, see, yes. Yes, you are right. So when we talk about the gap or the transmission line or some kind of interconnect, so let's take an interconnect between one chip to another chip or one circuit to another. So when we make a very narrow transmission line or narrow interconnect, we have lesser capacitance. So when we do everything on the same IC, there is we can create a very narrow metal wire between one end to another. But when we go for the hybrid integration, where we have to use some kind of wire bonds or some kind of a TSVs or bumps, they are more thicker. So they are more thicker, that's why they contribute more parasitics. So always when we have to reduce the parasitics in our design, we try to make it more compact. And more compact solution is possible in case of monolithic design, not in hybrid design. But again, there are different trade-offs that I will discuss. What is happening between monolithic and this hybrid. So, but in monolithic, the advantage is you can make a very narrow interconnect between one circuit to another. That's why you will get a lesser parasite. Yes. So yes. So the main parasitic way, the main limiting parasitic will come at this node, where you combine the photo detector with the TIS or the amplifier. That is a very critical node. So whatever the parasitic at this node will happen, it may be due to transistor layout, or it may be due to the interconnect length, or whatever. There will be some parasitic that is I modeled in terms of CT, and this CT will impact your bandwidth. If you have higher capacitance, you will get a lower bandwidth. So that is the main idea. So if you try to want more bandwidth, then you try to reduce this capacitance. So this capacitance, I will discuss. There are a lot of contributions from different components. This is just a model. It can come from the amplifier or maybe the device. Yes. So we have RF bond pads. So I will come. So this is how I show a monolithic, where you have a single chip, and this is hybrid 2.5D. PIC stands for photonic IC, and EIC stands for electronic IC. And you make a wire bond here. This is a gold wire where you can make an interconnect, right? So when you go for the monolithic side, the total capacitance you will get at the input is 20 femto roughly. This is the capacitance which is coming from the photodiode. Photodiode, it has one capacitance. So off capacitance, or we call this. This is around 20 femto. But when we go for the hybrid, what happens is there is some RF pad here, there is one pad here. They contribute a lot of parasitics. So if we assume RF pad has 30 femto, so 30 femto come here, 30 femto comes here, additional 20 femto from the photodiode. So it becomes 80 femto. So almost 4 times capacitance goes up because of this 2.5D integration. Almost 4 times means your bandwidth becomes half because it's square of 2. So this is how we try to minimize the parasitics between these two nodes. But there are a lot of disadvantages in monolithic side that I will discuss now. So let's take an example. I just dropped, earlier I have shown one equation, bandwidth and FT. So we have FT versus the bandwidth. I have shown one equation earlier. I just plotted the FT and FT, bandwidth versus FT. But in case of monolithic, I told that 20 femto was the capacitance and 80 femto for the hybrid. These are the graphs. So this one is monolithic, this one is hybrid case. So you can see monolithic, you almost get 110 gigahertz. Assume your FT is around 300 gigahertz. So this is the bandwidth you will get. And on the 2D integration, you will get only 55, almost half of the bandwidth you will get in this case. Let's move to one more type of integration. This is one. This is called 3D integration. Rather than placing 2 dies nearby, one die is kept on top of another. So this is how you can minimize the interconnect. So this, when we do this kind of a bonding, the capacitance comes out to be around 30 femto. So it is almost similar to 20 femto, slightly higher on the side, but lesser than the 2D integration. So this is how 3D integration can reduce lot of parasitics. And also when we go with the performance side, this is how the 3D will sit here. So the top is the monolithic, bottom is the 2D, and in the middle there is a 3D integration. So this is how you will get. But now I am showing the 3D, you can get 145 gigahertz of bandwidth, right? Ideally I should say, I have to see this point, but I am saying that with 3D you can actually get more bandwidth. Why I am saying? Let's see why I am claiming this point. So I am emphasizing this 3.145 gigahertz. It is more than monolithic side because I am considering higher FT. Let's see why. So what happens with the monolithic side? When we do the monolithic integration, when we fabricate the germanium diode with the CMOS, there are a lot of issues happen. So almost this is 10 times thicker urate oxide we need to use, and that's why because of integration of diode, there is a 20% degradation in FT happen, and that is due to the self-heating. So this is one of the major issue with the germanium diode. When you use a monolithic technology, you will somewhere compromise with the performance of the device, FET devices. This is about the silicon. This is only on the silicon only. I am talking about the silicon. What happens is when we, because of diode, germanium diode, we have to make this box, urate oxide box, almost 10 times thicker. If you don't want this one, then there is no need to increase the box. But when you increase the box is silicon dioxide, it's a glass. It is very poor conductor of heat. So when you are making more thicker box, more self-heating will happen. So that's why the device performance will degrade. Just introducing this device, your other device is impacting, or it is performance is degrading. This is what happens. Ideally, if you don't have this one, you will get a good performance in silicon. So people have started using the monolithic side, thinking that it will improve the performance, but eventually what happens is you are getting a germanium diode, but your FET device, your amplified performance is degrading. So overall, if you look around, it is degrading. So that's what happens. Now coming to this another thing, we have one more. We have shown the 3D integration. So in 3D, one of the other devices apart from silicon, CMOS, one of the major processes by CMOS. That is nothing but your HPDs or BJDs. So based on the TCAT study, so these are the different FT estimates of different foundry by CMOS process. So based on the TCAT study in the reference one, it demonstrated that when you have a BiCMOS process, BiCMOS means your HPD and CMOS together, your performance, your FT estimates will not reach more than 500-700 gigahertz. But if you fabricate only the HPD device, don't care about the CMOS device, don't fabricate the CMOS device. If you fabricate only the HPD device, you will get a more higher FT max. Because when you make two devices on the same technology, you will compromise the performance of one device. So that is what happened earlier. Now because of 3D integration in the recent times, what people are deciding that let's remove, right, earlier they want to fabricate everything on the same die, let's separate out. Let's make BJT on different type, let's make CMOS on different type, let's make photonic device on different type, and then we will do the 3D integration this requires a lot lesser cost because it requires lesser number of mass, it is easy to fabricate. So overall cost, including the packaging, it is reduced. So this is more effective solution going forward. So in going forward, when you talk about earlier I have shown one IC that consists of all the Qualcomm IC that consists of all the logics, all everything. But when you go forward next 5-10 years, we will have different ICs. One IC will be going for RF, one will be for logic, one will be for memory, and finally people will integrate into 3D integration, and that will actually reduce the cost and also give a better performance. So now what happens when we have higher FT max, right? When we use this FT max, and if we see this this curve, so because of 800 gigahertz, we can be still here. So rather than comparing here, we should compare at this point. Even though we are using 3D integration, we can achieve more bandwidth because we are fabricating the device and that the performance of the device is not impacted. We can achieve more out of that device. So this is how, even though we are using the 3D integration, the performance can be much better than monolithic side. That's why the people are going for 3D ICs and all these nowadays. So this is one, the TIA or the trans impedance amplifier we fabricated during my industry time. So this is very short feedback. TIA includes the input stage. There are a couple of gain stages and there is an output stage. And we compare with the hybrid versus monolithic, and we achieve a higher bandwidth because of lesser parasitics on the monolithic side. On 22 nanometer FinFET, because of higher parasitics, they are almost 75 parasitics are there, so they still get lesser bandwidth. So this is how we demonstrate this technology in the global foundries. And this is the layout and the chip photograph. We did model to hardware correlations, and these are the results we got in the hardware lab, which shows a good correlation between the model and simulations. And there are some innovations also we did on the inductor side. So this is inductors, coil inductor, how we fabricate in our IC design, like a spiral. It is done on the top metal of your IC design, and we fabricate. So the main idea here is we introduce some cavities in the inductors so that this substrate is actually a lossy substrate. The silicon substrate, the resistivity is very, very high, and it's a lossy. So most of your signal, the EM fields which is going through your substrate, it gets leaked out. So because of the eddy current losses. So when we introduce the cavities, these are the air cavities. So it is completely filled with air. So air has a lowest dielectric constant, as we know. So that's why we are getting a lesser capacitance for these inductors, and we improve the performance for the inductors. And then we use these inductors in our design. If you see, we get almost 6 GHz improvement in the battery. Just by introducing this cavity, we get this improvement. So this is how we did in this technology. Just for the demonstration purpose, I just so let's move to another case study. So till now, any questions? Anything up to now? So let us move to the next case study, that is wireless communication. So in wireless communication, the most critical block in your mobile radio receiver or any radio receiver is the power amplifier. We call this PA, and when we go with the higher frequencies, 220 GHz is the next big thing. So with many researchers around this world, they are working around these frequencies. So this is called deep band PA. So as we are going towards higher frequency, your dimensions, the lambda, as we know that it gets reduced, and you can achieve higher frequency with lower dimensions. So this is how the designs are reducing as we move for the higher frequency. But the major key challenge is the PA performance. So this is what at 220 GHz want to achieve. These are the desired goals, and this is what right now we are here. Almost 200 milliwatt of the power is the goal, and we are at the 20 milliwatt. So this shows that there are a lot of gap, and these are the theoretical lines, theoretical limits of the amplifier, silicon power amplifier, and the third. So efficiency wise also, it is not possible to achieve more than 10 or 15% efficiency from the silicon PS. So that is one big challenge in next. So you heard about the terahertz design, sub-terahertz design, imaging. Different applications are coming for wireless imaging and all those. So they are going to operate at the D band somewhere around 80-90 GHz. And at those frequencies, the power amplifier is the key limiting block where you cannot achieve more efficiency and more output power. So this is just to summarize. So as we are moving towards higher frequency range, so now receiver is less stringent, but on the other hand, the power amplifier, in terms of power efficiency, it is more difficult to achieve. And so how we are going to exploit the different packaging in this case? Just like in silicon photonics, we have seen that by introducing the 3D integration, we can actually improve the performance. Similar to that, in case of wireless communication also, we can use the packaging and we can improve the performance. So these are few recent papers. They demonstrated D-band or W-band power amplifier using different devices. So gallium nitride is one of the major technology which is growing recently. It is used for high bandwidth or the high frequency power applications for high power. So they demonstrated very good, almost 40% efficiency with somewhere half a watt power. So 40% efficiency at 94 gigahertz is a very good number, which is not achievable with the silicon or the CMOS technology. So this could be the one possible technology going forward for this application space. Right now in the researchers who are working in here, they are divided into two areas. One are working in gallium nitride, other are working on the indium phosphide. So in indium phosphide also, there is one paper came which demonstrates almost PAE of 15% at 152 gigahertz. So this frequency is more higher than the recent one, the last one, and it is almost half watt power from this amplifier. So this is again one competitive technology, indium phosphide and gallium nitride, which when we use in the 3D integration, we can actually improve the performance with these two. But what is the challenge? We have seen indium phosphide, gallium nitride. These are the good technology which can be used for high or sub-terahertz frequency, and they can offer better efficiencies and the better output power. But the major challenge is, if you see, these are the power thermal density. So when we talk about this, for example, take an example of a HBT, the BJT and the MOSFET. MOSFET have more number of fingers and it's more width in nature. On the comparison, BJT, the width is very less. So that's why the heat which is accumulated over the time, it will be more high in case of BJT than the MOSFET. So that's why if you see the MOSFET, this is the CMOS, where the CMOS, it has lower thermal issues, but when we shrink to silicon germanium, it will increase. And when we go to indium phosphide and GaN, it is more severe. So as we more progress towards the indium phosphide, it still can give you better output power, but the problem will be the thermal issues. So you need to come up with different ideas to remove this thermal management. So there are different heat sinks we use in our technologies to reduce the extra heats accumulated on the tank. So these heat thermal issues can create a very long reliability issues in a long time. So that need to be addressed. So this is very open grey research area where people are using different kind of integration schemes where they can sync out the different heating mechanism. They are trying to make different types of interconnect which can be used to sync the heating effects. So there is more innovation is going on in this packaging space. And this is a very intuitive diagram to show you going forward. This is the limit. We just put that. This is the sub-terahertz area, and this is what right now 5G and millimeter wave we have. So if you clearly see, the CMOS will not able to come up in the sub-terahertz. Silicon germanium, because of its property, it will be just managed to commit. But for the next big thing is the third and fourth group element, that is indium phosphide and gallium nitride. So that will do a much better role when we go for this sub-terahertz applications. And these could be fabricated only when we have a 3D packaging, because indium phosphide, everything you cannot do on the indium phosphide. Suppose if you want to design a logic, memory, or some high-speed analog design, you don't want to utilize these indium phosphide. They are very costly technology. You need just for the power amplifier application. So what is the optimum solution is you design a indium phosphide or gallium nitride PA, and you have a different blocks in the different CMOS technology, and then use the 3D integration techniques. Then interconnect, just put one die on top of other and do an interconnect between them. This is how in the next 20 years semiconductor industry will go. So earlier there was time when people started all the things together in the same silicon area, but finally they realized that when we go with a different type of device in the same silicon, the performance of each device impacts the other device, and they are not able to get the best out of it. So the best possible would be that when you separate out the things, make different ICs and then do the 3D integration. It is actually lesser costly, cost-wise also it is economical, and also it gives you performance benefit. These are the conclusion points just for the, so as we are saying that beyond 22 nanometer we see that the performance of the RF device will get saturated. Now to satisfy the Moore's law and Adam's law, you need to go with the 3D integration. So there is a limit. You cannot increase more transistors on the IC when you go with the 3 nanometer, 5 nanometer device. You need to go for 3D integration. So 3D integration is one way where you can increase the number of devices or the number of transistors over the same area. And then we have seen that if you try to accommodate all the devices, all the different devices in the same IC design, it will impact their performance. So let us not cater everything on the same plate. Let's distribute it. Let's make different devices for different application and use the 3D integration. And we have seen that 3D integration not only gives you the performance cost benefit, it also have performance benefit. Because when you make a device, standalone device, like HBT or CMOS, it has higher FTF max compared to the BiCMOS process. So this is how next going years we will see indium phosphide and GaN and silicon germanium will play an important role. But the major challenge would become is the thermal issues, thermal management. So these devices cannot tolerate higher heating effects. So your devices will get heat up easily. So there could be different areas or different mechanisms we need to do going forward where we can sync up all these heating issues to perform or to integrate the devices. So this is all from my side. I would like to know if any questions are there. Let us, apart from the slide, you are free to ask any question. Anything? Yeah. Analog? Right. See, the analog processing, why basically all the signals are analog in nature. See, when you go with the digital, right? So we require the information. So it will be given in either ones and zeros in digital form. But when we talk about the analog, it's not only the amplitude, it also has a frequency, it also has a phase information. So when we transmit, right, we transmit in analog form. Even though if you see, when we're transferring the wireless over the antennas, we modulate the signal into the carrier because we need the carrier. Otherwise, we cannot transmit that. Direct digital signal we cannot transmit into the air. We require carrier signal. So that's why everywhere you will see analog signal. So I always say that analog is not only the sinusoid, it also a square wave. Because it's not only the square wave, it's not only ones and zero, it also has a frequency. It also has a jitter. Not all the square waves are properly shaped. If it has a jitter, the crossings will change, right? It is also an analog signal. When we talk about high-speed square waves, right? Suppose you have a 20 gigahertz, 30 gigahertz square wave signal. If you observe it in the spectrum, right? It doesn't have. It will have different harmonics. So it's not purely digital signal. Purely digital signals are static signal, I would say. You apply 1, it will be 1. You apply 0, 0. These are pure static signal. But when you have a high frequency signal, in terms of, let's say, your PAM4, NRZ signals, these are high frequency signals. It's also a mixed signal design or analog design. It's should not fall in the digital form. So this is how analog is important, because it contains a lot of information. You cannot transmit directly in the digital form. Anything related to VLSI? Any questions? Anything you want to know? I think the presentation has a lot of jargons or a lot of keywords which you are not aware of that. But still, if you have any questions, I would like to answer. Yes. So nowadays there are a lot of importance are giving on the open source. So there are a lot of paper which shows, like ngSpice we have, Magic is there. So there are different tools are there right now. Yes, you can do. Right now there are a lot of EM simulation also. There are some open source tools are there which you can do EM simulation, electromagnetic simulation also, RF simulation also you can do. These are open source. So there you can use that. Spectrum analyzer, network analyzer is one thing. So they comes up different frequencies. So start from 1 gigahertz. Yeah, they come up to 110 up to. Okay. Yeah. Okay. Right. For RF also they comes in different frequencies. 6, then I think 12, then 18, then 40. In that range, the cost will increase accordingly. So that's how it is. See, definitely, if some student, if any collaboration is there, we have testing facility. So we can do the testing, or if you can contact HODs or the concerned faculty, and you can request what are your requirements, or what you need to come up with a test plan, what actually you want, and what you are testing. If we have a pre-defined plan, then definitely we will get it. We will allow. Because testing is something, some testing facility as a new IIT we don't have, we are acquiring. So we also depend on higher IITs or different IITs. So this is how we proceed. So if you have any plan in future to test some circuit, you just come with the plan. So this is my circuit, this is the experiment I want to do, these are the results I want, and what frequency you need to cover. So if you give a plan and all the things will be there in the lab, then definitely we will. Anything? No, 5G is up to sub 6 gigahertz, right? Gigahertz. No. So the tower to tower, you were saying backhaul communication. So these are the backhaul communications. They are not up to that range also. Still lower range. 2000 is very high. 2000 no circuit. 1800 gigahertz. It is not work. No, it's not. 1800 is you cross the terahertz. It's more than. You cannot. No, you can. No, how they are transferring on the wireless they are transferring. How do you generate? You don't have oscillator for even 1800 gigahertz. You cannot generate that. No. Won't be possible. So people are struggling to generate even 500 gigahertz oscillator. So finally, if you are talking about 1800 gigahertz, so it's not there. And any other question? Students, I don't have any question from students. So all are from third year or fourth year? Final year, right? So most of the things I covered, the MOSFET basics, I think it's done in your course or something, right? So amplifiers, op-amp, you are familiar, right? So can anyone tell me what is the difference between op-amp and OTA? Operational transconductance and op-amp. What is the basic difference? Anyone? Okay, BJT is what type of device? Can anyone tell what is the difference between BJT and MOSFET? This is very fundamental. You should answer this. The difference between BJT and MOSFET. Current control and voltage control. Okay. Any other difference? Anyone knows? Any other? Yeah. Biasing obviously is different. Any other? Very basic. Speed is okay. Speed I think both are all comparable because it depends on FTF, so we have MOSFET. So one major important factor is, apart from all these differences, the self gain, intrinsic gain of the device. So in the MOSFET you will not get high gain, but in BJTs you will get higher gain. Okay.
On behalf of the Department of VC of Narayana Engineering College, Gudur, I express my heartfelt gratitude and thanks to Sir for having made it to come here and deliver his valuable speech.